mark. Just a quick announcement. I'll ask Pancake to put it on the class website. Saturday, 10:30. 10:30 to 12:30. Come to the Warren Hall area. I don't know which classroom. We'll find one over there. And we'll go with it. 10:30 to 12:30 Saturday, we'll have a class, And homework for, I think, is out. You can bring it back next Tuesday. We'll hand you the home. I'll try to finish the chapter 5, hopefully by Saturday, because we don't have much more time. We have 2 more sessions after Saturday. It's going to be the next Tuesday, Thursday is the Thanksgiving, and the Tuesday after. We have only 2 sessions. So we'll hand you the homework number 5, before Saturday, and the due date for the following week. But I'll give you the homework number 6. We'll do 2 or 3 problems, not more. It's about a per-unit system, similar to what we have had before, but a little bit different. We call it system modeling. It's not in the chapter of the book. I'm going to cover it myself. But you can find it in different power system books. And that one will be due until the end of the final week. Funpay will set up a time. You guys will come, and Friday sometimes, we drop your homework, So this is about the homework. 3 more homeworks. 1 is already out. You have made it, and 2 more coming very soon. Yeah. It's very simple problem. Just check them. It's a very, very simple problem. Just I want you to practice different one, not all of them. But they're very simple. Just look at them. They're very, very simple. Especially I want you to look at problem. I don't know what problem they are, but they're all from your book. The reason just I type it is because some people, they don't have a book. I want them to have the question. But if you look at it, one of them is problem. All of them, they're from the book. But one of them is problem 27. And the other one is problem, if you need help, first read the book. Not the book, just the question in the end of the chapter. Because before asking to calculate this thing, they explain it, how to do it. Problem number 27 and problem number 48. Check these 2 problems, from the book, I'm saying first. And I'm not sure how much you put in the homework, but read it, from the book, that part is said how to calculate this kind of thing. Yeah. Tuesday. Homework 4 will be due the next Tuesday. I'll try to grade the exam for Saturday. We'll bring it Saturday, and you say 10:30, right? I was thinking, we can wait stay after the class. The game starts closer. So I'll bring your papers, Saturday, and I may come like 10 o'clock here, so you can come see your papers before the class, But I'll let you know Thursday, see where I am, or I'll send you an email to make sure I have the midterm group grade. So 10:30 Saturday is the makeup class, and we don't have the class the last Thursday of the final. So any question?
Saturday is in this room?
No, we're going to go to Warren. I'm not sure what's the class, but we'll go to Warren Hall over there. I think we'll find the classroom over there. You'll find the classroom over there. I don't know. Do you guys, know any of the classroom, the bigger one? We can say it right now to meet over there. 2005?
Are they going to be locked?
Huh?
They're going to be locked, right?
Oh, they're locked?
Yeah. You sure?
Oh, they're locked, so I didn't know that. So how are you going to get to class?
We'll prop the door open on Friday. Prop the door open on Friday.
How?
Put some gum in it.
Tuesday of the final week there is a class, but Thursday you don't have to. The final the example, not that, we're not talking about the example. I'm talking about the week before the final exam. So we're supposed to be here. Any other questions? Okay, let's just continue. We went through the calculation of the capacitance for the two-wire system and three-phase system. I want to finish this capacitance, transmission line parameters today, and we start with the transmission line model. And one question, do you guys know about the 121 if they opened it up for registration?
No, so we can't wait this long.
Everybody's waiting?
Yes.
Why? You know, why? Huh?
So we can enforce 188.
Oh, they want to enforce that.
No, because they didn't set the last time, so.
Then they don't have to watch that.
They didn't say what?
The watch times?
What time?
Lab.
Oh, last time. No, okay, last, okay. Yes, yeah, because someone sent me an email asked about that. And, okay. So, we talked about the single-phase system and three-phase system. You know, like the inductors we talked, if we have a bundle conductor, you know, we will have a two. Before going to the bundle, you know, the one we calculated, it was a three-phase. We did not talk about this. We had a three-phase equal distance. D, and D. We calculated the capacitance for this one. Now, if they are not equal, what should we do? Right? Like the one we had for inductance. Let's say we have a three-phase like this. Right? So this is phase A, phase B, phase C, right? We want to keep the system balanced, right? All the phases they see the same capacitance. What did we do for the, let's say this is the A, B, and C. How did we fix this problem? They are not equal distance. You say transposition, right? Transposing, right? So basically we'll bring A here, B here, C here, for the same length here, right? This one, and after that, that one. And again, we did this one. We brought this one here, and this one. Basically, all of them, they are in the same CN. We got it to this value, 2 pi epsilon over ln of d over r. Let me say something else. You know, one of the exam questions is going to be about, you know, calculating. I don't know, we'll give you kind of, you know, conductors, just kind of calculate the inductance, calculate the capacitance, those kind of things. There is no, let's say, things tricky about that. There is nothing. The only thing is you should practice. You know what I'm saying? You should practice and you learn this equation. Because if you don't work with this equation, you know, yes, you can go through the equation during the exam and find the answer, but it may take 1 hour or 1.5 hours to finish the question, you know. The only thing about the question for the final exam, for this part, you don't need any creativity. You just need to know those equations for single phase, three phase, capacitance, and, you know, inductance, those kind of things. So be careful if somebody asks tools question. I put it intentional tools. You guys practice as much as you want, you know. So exam is going to be something similar to one of these questions, you know, not exactly the same, but very similar to this. So this is for three-phase system per minute, right? That's what we calculated from the, that was the last thing we calculated in the in last week. Now let's go to the, if we have a three conductors, they are not equal distance. If we have three conductors, they are not equally distant. For example, we have A, B, and C. So this is the DAB, this is the DBC, and this is the DC, right? So what we did here, we came up with a D equal, right? How much was the D equal? We said, okay, we're gonna go DAB times DC times DCA is square root of 3, right? Kind of averaging, you know, if you remember from the inductance part, here is gonna be the same thing. Again, for this kind of thing, which they are not equally distant from each other. But with the transposition is happening, you know. If the transposition is not gonna, it doesn't happen, the system is not gonna be balanced. With this kind of thing, again, CAN is equal to CBN is equal to CCN is equal to 2 pi epsilon over ln of D, the D equal over pi. Farad per meter. And D equal is DAB, DBC, DCA, very, very similar to the inductance calculation. If you look at it, very, very similar to the inductance calculation. So, this is a three-phase system, not equally distant from each other, but fully transposed. The next thing we had in the inductors, what was the next? If you remember?
Yeah.
What was the next? They were bundled, right? Each phase was like a 2 conductor or 3 conductor or 4 conductors, or could be as many as 8, 9. But usually they don't go with that. Why? We talked about this one. We could have a 2, we could have a 3, we could have a 4, or you could have more. You could have, think about it. Consider a circle here. 4 is going to be here. This is the 4. 3 was like this. You could have 6, 8, 9, whatever you want. But usually, this one you see very, very rarely. Mostly you see this one, or maybe this one. This one I was driving to Irvine during the week. There was a nuclear power plant over there. I cannot pronounce the name of
San
it.
Onofre?
San what?
San Onofre?
Yeah, that one. So if you look at over there, if you look at the cables coming out of the power plant, it's this one. They have this one. Next time we are traveling over there, just check the cables over there. They have the bundles of 2 wires over there. You can see it. You know. Why usually they don't go with this one or this one or 5 or 6? Why? Why? Huh? It's one?
Safer?
No. It's more expensive. You answering loud? So it is more expensive. When you put the more 3, 4. So the cheapest one is just to keep 1, right? If you get to somewhere, you have to put too many of this one, they go for 2 circuits. They put 1 circuit on the left, 1 circuit on the right, 2 3-phase system. They do that one. They kind of share the power that way. But the maximum I have seen is 4. Theoretically, you can go to as many as you want, you know. But the maximum I have seen in my life is 4. I don't think that there is more than 4, you know. But mostly I have seen 2. 2 is very usual. You see this one very normal when there is a high power. You see that one. 3 I have seen it also, but not more than 4. Now, we're going to see if we have a bundled conductor and not equally distant from each other. Basically, if you have something like this, each of this one, for example, this conductor by itself is something like this, for example. D. Right? Or it could be 3 conductors, or it could be 4 conductors, or it could be 5, whatever number of conductors, right? So we want to see if this conductor, they are bundled, what is going to change? Basically, this equation is going to stay the same. Which part is going to change? This part, right? We need just to calculate the new arm, right? So if you go with the previous method, we calculated the GMR for the inductance. Here you can do the same thing again. So if we have a 2 conductor, I think we will call it DS. Let me see if we call it DS. Yes, DSC. If we have a 2 conductor and a distance d from each other, DSC is PSC is going to be the square root of R times D. R is the radius of this. This is the R. And the capacitance is going to be C, for example, AN is going to be 2 pi epsilon ln of D equals divided by DSC. Farad per minute. If you have a 2 conductor. If you have a 3 conductor, this is exactly like an inductance part, you know. And distance D from each other, and the radius is R, DSC is going to be square root of RD2. Root 3. And the C is going to be this. Just replace the DSC with this number. If you have a 4 conductor, this is the maximum distance we have to. They are distance D from each other. And the radius is R. DSC is going to be 1.09 root 4 of RD3. So, if we have a conductor, 3-phase, unequally, you know, this is spaced from each other, we need to calculate the D equal. If each conductor is built from based on bundle of conductors, we calculate the DSC using this equation. Now, you hear maybe about the charge current for example, the system. Let's say what's the charge current. Let's go back because you see it in the homework. Let's go back to for example, single phase system, right? We had a conductor X, we had a conductor X, and we had a conductor Y, right? We have a conductor X and we have a conductor Y. What is the charge current? You know, for now I assume this conductor, there is no impedance, where like a Z and R and those kind of things. Just because I want to just talk about the charge current. I can model this system. This system is going to be like this. 2 ideal wires, right? And how much capacitance between them? CXY, right? CXY. So the charge current is going to be this current. And if this voltage is a VXY, right? If this voltage is a VXY, so how much is the IXY or I charge current? Basically, IXY is going to be VXY times YXY. Y is the admittance, right? Or you can say V divided by Z, right? And how much is the YXY? How much is the YXY? YXY is the CXY. CXY. This is the per. This is the, again, positive charge Q. And this is the H. This one was, the distance was H here. We are going to have a negative charge here, Q minus. So basically, if you look at here, the magnetic field, and this is the H. And if you look at the electric field, it's going to be like this, going this way. It's going to be like this, coming here, going this way. It's going to be like this, coming here, going this way. Here. If you compare this one and this one, just comparing these two, the same as so basically this system, there is no minus Q. There is no minus Q charge. But this system, the electrical field here generated is the same as the electrical field generated here. So what's the advantage of that?
You have to do one per
If instead of using the system on the left, I can use the system on the right to calculate the electrical field, right? And say these two systems, they are the same, so I use the electrical field for the left side. I calculate it from the right side, but I use it for the left side, right? Now, why this one is easier? Why this one is easier?
Because you can use the two-line approximation.
We went through this one already, right? We had a two-wire Q minus Q, right? And we calculated the voltage, we calculated the capacitance and everything, right? So basically, instead of having a distributed electrical charge here, see, this is a distributed, you know, it's going to be, I don't know, 0.1, 0.1, 0.1, 0.1, it's going to be continuous. It's going to be a distributed electrical charge. Instead of dealing with that, I'm going to deal with this. Two central electrical charge, right? And with these two, I know exactly how to calculate it, right? Basically, I'm coming in with a fake electrical charge, right? With a fake electrical charge, which is going to give me the same electrical field, right? Which I'm going to use for my capacitance calculation. Now, considering this idea in mind, let's go to the two-wire system to see how we can calculate the capacitance. So did you get the idea here? Let me say it one more time. This is the concept is very important because it's very important because the calculation is very simple. I said we have a charge, and assuming the ground is a perfect conductor, is going to induce the same electrical charge, but with the opposite, you know, sign to the ground. So basically, we are going to have an electrical field here. Now we need to tell this one is going to affect our capacitance, right? How? How much is going to affect us for capacitance? We need to see how it's going to affect the electrical field here. To calculate the electrical field, we use we call it method of images, you know. So we said, okay, we're going to come with the image electrical charge of this image. This is kind of the axis, you know, image respect to this one. We said this system is going to create the electrical field here, which is the same with here. So if I can calculate this electrical field, calculating the capacitance is easy. Because I calculate the voltage, and after the voltage, I use the C is equal to Q over V, right? Which we did. Now, this system is very simple. Why? Because it's a two-conductor. Right? We had Q and minus Q. Already we did solve this problem, right? So now I'm going to use this idea and go calculate the, for example, impedance capacitance of the two-wire system with a ground effect. We call it the ground effect. And one of the homeworks I said, I think it's problem 48, something like that, I said, that's a three-phase system with a ground effect. And as I say, if you go to the book, it didn't discuss it during the chapter, but even in the problem section, you know, it explained it before, you know, asked you to calculate the capacitance, you know. Look at that part to see how you should calculate the capacitance for a three-phase system with a ground effect. Now here we're going to go through the single-phase system, two wires. So basically, we have a two conductor, X and Y. X and Y. This one has a Q charge, this one has a minus Q charge, right? Let's say the distance from each other, we call it dxy. Right? They are dxy from each other. And call it D, let's call it D. And the radius of each one is R. These are R. Radius is R of each of these ones. And we have a ground here And this guy here above the ground, h meter, right? You want to know how much is the capacitance for this system. For the two wires, you know how much it is. How much was it? Here I should have it. 2 pi epsilon over ln when I had a 2 wire d. We say was a 2 pi epsilon over ln of d over r, right? We had that. Without the ground effect, no ground effect, we had Cxy was 2 pi epsilon I believe over how much? I'm checking. This is for 3-phase system. For the 2-wire system. I think it was a it was a pi epsilon. Yeah, pi. And then d over r. With no ground. Now, we want to see how the ground is going to affect this. So basically, based on what I said here, we're going to have one more charge here. Let's call this one, is it going to be positive or negative? First of all, negative charge, right? This one is going to be minus q. And this one also is going to have an image here. How much? This is negative minus q. This one is going to be positive q, right? And how much is this distance? This is h. This is d, right? So basically, there's a four conductor system now, right? 4 conductor system. I'm going to calculate the Vxy now. Previously, we calculated Vxy based on just this q, right? Now we have to calculate it for this system. Let's call them, give them names. That one was the Vxy. Let's call this one. Let's call this one x prime. Let's call this one y prime. So this one is going to be dx prime, right? This one is going to be dx prime y prime. This one is going to be dx y prime. And this distance is going to be dx prime y. And this one is dy y prime. Right? We have all this distance. I'm not sure what notation is used, but yeah, they use the same. Yeah. Now let's calculate. So to calculate the capacitance here between these two conductors, what should I do first? I have to calculate the voltage, right? If I calculate the voltage, I'll say C is equal to Q over V, right? Let's calculate Vxy. So Vxy from equation, let me go read it back. What is equation? Equation 486. This is what we have. It said Vki. This is what we have. Is sigma 1 over 2 pi epsilon sigma I is from 1 to n qn ln of dim over dkn. This is what we calculated before. When we have a m electrical charge and we want to calculate the voltage difference between 2 points, right? That was the equation. Now, I want to calculate the voltage difference between x and y. Let's start to write it down. Basically, the capital M is what? Is 4, right? We have 4 electrical charge now. 1, 2, 3, 4, right? Let's start with that. So basically, if I use that equation, it's going to be 1 over 2 pi epsilon, right? Let's just write from the first one. So this one is number 1, number 2, number 3, number 4, or x, y, x prime, y prime, right? So I need to remember this one was the negative voltage, right? And this one was the positive voltage. This stands for the positive voltage, right? So we are going to calculate Vxy when we are considering x is positive, y is negative, right? Let's calculate the voltage between these two because of this charge. Because of this charge. So how much is going to be? It's going to be Q, right? I'm going for this one. I'm going for this one. I want to see how much voltage I have here if I had only this electrical charge, right? So it's going to be the electrical charge. How much is it? Is Q, right? Times ln of the distance of the electrical charge to the negative sign, right? I mean, see, this is negative. I'm talking about the voltage. It's the plus minus Vxy, right? The distance of this electrical charge to the negative sign. How much is it? Dxy, right? So it's going to be dxy over to the distance of this charge to the positive of the voltage. What is that? Dxx, right? The distance with itself. Dxx. We went through all these things, before. It's not new, You remember this thing, right? Last week we went through all these things. Dxx. Which dxx is the radius of this conductor, right? Now, let's go to this charge. Let's go to this charge. I want to see this charge, how much voltage is going to generate, right? So first of all, what's my charge? Minus Q, right? So I should put it plus minus Q times ln R. Now, you tell me, what should I put in the numerator? I want to see how much is the difference voltage here because of this electrical charge. Should be dYy over what? Dxy, exactly. Now let's go to the third one. This one. Here. How much is the voltage difference here because of this one? How much is it? First of all, the electrical charge is minus Q, right? Plus minus Q times ln of, you tell me, what's that? I want to see the voltage here, the voltage generated here because of this charge here. Should be dx prime y divided by what? dxx prime. They're calling d, I should call it. You have always one x. So it's going to be dx prime y divided by dxx prime, right? Plus the last one. Tell me the last one. Plus how much? Q positive. This one. dyy prime, exactly. dyy prime divided by dxy prime, right? Now, let's simplify this thing. So these two together and these two together. So Vxy is going to be 1 over 2 pi epsilon. So I'm gonna factor in a q for all of them. So this one is going to be ln of this one minus this, right? So basically minus this one reverse is going to be dxy over dxx dyy. Next one. Minus, let me see what, how do you put it? Minus or plus? I think it's minus. Ln of, I'm going to write it minus ln of. Dx prime y over dxx prime minus dyy prime over dxx prime. So it's going to be dx prime y dxy prime over dxx prime dyy prime. Now let's replace this. dxy is equal to how much? D. Basically this one is going to be d squared, right? This one is going to be how much? R squared, right? Because dxx is R, dyy is R, right? How about the dxx prime? How much is the dxx prime? 2h. Dxx prime. It is the 2h. How much is the dyy prime? 2h, right? How much is the dx prime y? Or let's not do this one. Let's not do this one. Let's do this one. I'll simplify that there. This one, dxx prime is equal to dyy prime, right? Both of them, they are 2h. dxx prime and dyy prime, they are dxx prime, right? And this one, here, dx prime y is equal to dxy prime, right? They are the diameter of this rectangle, right? They are equal, right? So basically this equation is going to be, and before doing this, this one also is going to be dxy to the power of 2. This one is going to be dxx to the power of 2, right? So basically it's going to be vxy is going to be q over 2 pi epsilon. So this is dxy over dxx to the power of 2, right? So the 2 is going to come here. Let's try it. It's going to be ln of dxy over dxx to the power of 2 minus ln of dx prime y or xy prime divided by dxx prime to the power of 2, right? This 2 is going to come here, this 2 is going to come here, it's going to cancel with this one, right? So basically, this one is going to be q over pi epsilon ln of dxy over dxx minus ln of dxy prime minus dxx. So I calculated the voltage. See, this is the advantage of the method of images. See, easily I calculated the voltage between these 2 points. Right? I know how much is the voltage between these 2 points. Now I have the voltage, I can calculate the capacitance. How much is the capacitance? So Cxy, mu Cxy, that one was without ground effect. This is with ground effect. It's going to be Q divided by this, right? Q divided by Vxy. So basically Cxy is going to be, Q is going to cancel this one. So basically it's going to be pi epsilon over ln of dxy divided by dxx minus ln of dxy prime divided by dxx. Sorry, this is a dxx prime. This is a prime. dxx prime. Right? Compare this one with this. Let me do it one more time. Now, dxy is d, dxx is r, dxx prime is 2h, and I'm going to write it here. dxy prime, how much is the dxy prime?
Square root of d squared plus
This one.
2h
It's going to be this one to the power of 2 plus this one, the square root of this one to the power of 2 plus this one, right? Basically is the d2 plus 4h, right? Now let's replace them here. So it's going to be pi epsilon over ln of d over r minus ln of dxy prime is this one. Let's say, I'm going to simplify this. This one divided by that. d2 plus 4h squared. That's divided by 2h. Let's get this one inside. It's going to be d2 over 4h squared plus 1. Okay. So basically it's going to be ln of d over 2h to the power of 2 plus 1. Farad per meter. Farad. So, the last thing for this chapter, I want you to compare that one with this equation. Which one is bigger? That one is bigger. Why? Because there is this one minus something, right? The denominator is going to be smaller. And so the capacitance is going to be bigger. So in general, with the ground effect, the capacitance is bigger. But let's look at this. What is affecting here? If, look at these two, right? Just I want to say, if the H is much bigger than D, right? If the conductor is very, very hot, right? What is going to happen? D over 2H is going towards 0, right? It's going to get very small, right? So that thing under the square root is going to be almost 1, right? Basically, ln of 1 is how much? Is 0. So basically, it's no different from here. My point is the conductor is very hot. The distance of the conductor with the ground is much, much bigger than the distance between the conductors. So basically, there's no ground. The ground effect is almost zero. But in general, we'll go through some examples. This one is not going to change the number significantly. For example, it's going to change it maybe 1%. You know what I'm saying? This thing here is going to cause the capacitance to be like 1% more, or maybe 0.5% more. That effect is this much. It's not like maybe like a 10 times. You know what I'm saying? Or 2 times. No, it's not like that. It's a little bit, increasing the capacitance of the conductor between the conductors. The three-phase system with the ground effect is a problem for the 8. I'm not sure from the book, but I'm not sure which one is in the homework we put there. We put it there, but one of them is the calculating the capacitance of a three-phase system with a ground effect. Equation is there. They give you equation, but three-phase is as simple as this. Look at here. When you have a three-phase, let's say this is H, right? So it's going to be 3 here. Right? And you calculate for 6 conductors. So 3 conductors, calculate for 6 conductors, right? So my point is there's no difference. There's a little bit more calculation for 3 conductors. But the equation is given in the book, in the problem 48. Any question about this chapter? Let's summarize what we went through this chapter. We said how we can calculate the resistance of a system. We had this resistance. You're familiar with that. That one is the rho L over F. and this resistance changes with the temperature. But we have an AC resistance. There are different effects on the DC resistance. One is that if you look at the conductor, they are not a straight wire. They are kind of twisted wire, right? The effective length is, if you have 1 meter of cable, the length of the conductor maybe is 1.2 meter, right? That's one reason why the AC resistance is bigger than the DC resistance. The other one was the Hall effect. Hall effect, the current going through the surface of the conductor is going to reduce the A. So basically, the effective resistance is higher. We talked about that, and we said it does change with the temperature. That was the first one, resistance of the conductor. After that, we talked about the calculation of the inductance of the conductor. Is it 2-wire, 3-wire, all those kind of things. And after that, we talked about it, how we can calculate the capacitance of a 2 or 3 phase, single phase or 3 phase system. So basically, transmission line, either there are 3 phase system. So now we can calculate R, X, and R, L, and C. So basically, we can come up with a model for the transmission line. Now you know this kind of thing. The next part is now, we're looking at it as a, let's say, sub-level system. We're looking at how much is R here, how much X is here. Now in the next chapter, chapter 5, we are going to look at, okay, we have a transmission line, it has this much RXC, LXC. Now I have one source here, I have one source here. I want to know what's going to happen here, how I can transfer power, how I can model this transmission line. And this is the next chapter 5. We are going to start to talk about that. There's one thing though, let's say transmission line. Oh, I remember. In the homework 4, I'm not sure, did you attach the table 4 to that, the homework 4? Yeah, please do that. You know, when you guys look at the homework 4, you should kind of re-upload it, you know. Table 4 of appendix, it gives you all the information about this conductor. You may need those ones, you know. So basically, the GMR for the conductor, usually you don't need to calculate those kind of things. If you go look at table 4, for example, we call, I don't know, conductor Drake. You know, that's the name of the conductor. If you go to look at that table, you will see, okay, this is a Drake conductor, go through that row, and say, okay, the R is this much, I don't know, the GMR is this much. I'll give you all the information about that conductor. This table is a standard table, you know. The conductor they are used in industry, they are not kind of, you know, for example, I want to put 5 here, 6 here, they are all standard. Table 4, she's going to attach it to the homework, you know. So basically, those ones, they don't have a book, they can see the table. But if you have the book, it's in appendix, you know. You can find the table 4. It gives you all the information about the conductor. They are used in transmission line. GMR resistance, all those kind of. You can go look at it and let's investigate it, you know, to see what they are practical. That one is a practical. If you are going to design a transmission line, usually you go to that table to select the conductor. You are not going to come sit down. Okay, this is what we are going to do in the discussion session. I said, hey, we have a conductor is like this. Go calculate the GMR for this one. You know what I'm saying? When you are designing a new, for example, transmission line, you are not going to design a new conductor. You go to this standard table of the conductors and you select, hey, I'm going to select this conductor because it can carry this much current. I will select this conductor because it can hold this much voltage, right? But we are going to go through this chapter to show you how we can calculate those kind of things. And one day, maybe we need to come up with a new conductor so we know how to design it. We know how to get there. But table 4 gives you all this information about this conductor. Now go to chapter 4. This part is the easy part for the final exam, just to let you know. As I said, there is nothing, you know, to play with and say, okay, to make it a little bit free. This one should be 100% you should get a grade for this one. Just I'm telling you, you know. If you are not getting the grade for this one, it's because of you. Because there is nothing to no, we're in three-phase system, I can go trick it a little bit, you know, I put something there now, I have to think about it, okay. So if it's this much power, it's going to be there or something like that. This chapter doesn't have anything to play with it, you know what I'm saying? It's gone very, very straightforward. Just there's some equation, you can bring the equation, you have a cheat sheet, just you go calculate those things. But if you don't calculate then this simple equation, you know, later what was wrong? How should I calculate this one? How should I calculate that one? This is just practicing, you know. If I am you and I'm worried about my grade, you know, this is the easy part to get the grade. Transmission line. Transmission line, we have three different models. You know, they call it short model, medium, and long. Short, medium, and long. But in reality, the long model is the most accurate one, and it does work. It works for all the other ones, for the short and medium. But you are going to see, not today. We're not going to get to the long model today, but Thursday we're going to get there. That one is pretty complicated. There are lots of calculation, lots of differential equation to get there. But somehow we came with a simple model. You know, say if the short line less than 80 kilometers. How many miles a day? I think it was 50 miles, right? Less than 50 miles. They call it. You know, they use the short model. But it is kind of a special problem. You know, just to tell you, it's kind of a special problem. You're going to set something special. You cannot use this model. You have to go do exactly what we are going to do for the long model. You know what I'm saying? Because that one is going to go through the partial differential equation to get the model for the transmission line. But for the systems we have, there is a short, there is a medium, and there is a long model. You know, the long model just let you know. I'm not going to give you an example. What in homework they're going to say very clear. There is a lot of calculation. You know, you'll see there's I don't know how much calculation. And I don't want to, I'm not checking your, calculation skills. Now I want to check your power system skills. Just to tell you, I'm not going to give you the example. You know, the transmission line we're going to have in the final. Long model is not going to be in the questions, you know. But we're going to go through it. Because it's very, very important to learn how to work, to model the system, you know, with the transmission line, the long model. So, let's say transmission model to transmission. Model. So, what I'm putting here, this is more for one phase. But think about it here, see? Because this one is didn't explain it in the book, you know. The first maybe 10 pages of this chapter is talking about different things. It's pretty interesting, but we're not going to talk about that. Go look at it. There is an HVDC light. There is a voltage converter. These are something you will learn in power electronics too. And over there, when you learn those things, oh, there's an application here, even the high voltage. But I'm not going to go through that one because they're kind of advanced topics for, they call it HVDC, high voltage DC. But this is a power electronics combined with the power system. We're going to focus on the power system side here to come up with a model for the transmission line. So basically, a three-phase system, you have A, B, C, and either there's a neutral or there's a fake neutral, right? Or there's a fake neutral. So basically what we do is, okay, so we are going to have an A and B and C and. We can treat this system like a single phase system, right? A and neutral, or B and neutral, or C and neutral, right? So basically I have two coming here. Let's say I have a voltage here, right? Right now I don't know how to model my transmission line. There is a box. This is my power plant here connected to the transmission line, right? For example, phase A. Going through this transmission line. And here is my, let's say we call this one VS, IS, sending it, and we have a VR, sorry, IR, VR, right? They call it two-port system. You know this comes from electrical circuit, right? It's a two-port system. Transformer is a two-port system. There's an input, output, right? One port here, for example, here we and there is another port here, we call it receiving. This is a transmission line. You put your power plant here, right? This is the input port. And here we have the CD, which is a load. This is the receiving end, or is the load port, right? So there are two ports. They call it two-port system. This two-port system usually they represent with a matrix A, B, C, D. Let's see what is this is from circuit theory. No, this is all reviewed from circuit theory. I believe you have had this one, right? You guys know about two-port system, right? This is a very, very simple concept. It's not very, very complicated. But let me write it down here. We have a two-port system. So basically we said VS IS is equal to A, B, C, D times VR I. Basically, if I know this ABCD, which is in this case for us is a transmission line, right? Is a transmission line. We need to calculate ABCD for this transmission line. For somebody else, maybe it's a transformer, right? For somebody else, maybe is, I don't know, is a gear ratio, is a mechanical system, there is a gear here, right? But this parameters, they're not voltage and current, they're torque and speed, they're going to change. My point is a two-port system. This is my transmission line. I need to go calculate this ABCD for my transmission line for the short model, medium model, and the long model. Now, if I have ABCD here, basically I can calculate my VS is AVR plus DIR, and IS is going to be CVR plus DIR, right? For example, at the end of my transmission line, I say, hey, I want to have a voltage 60 kilovolt, I don't know, 200 amps, right? How much should my generator, my power plant should give me, right? If I have this model, I can go calculate the voltage and current of the generator, and I say, okay, generator should give me this much voltage, this much current, this much power, right? So, if you can see, A and D, they are unitless. There is no unit for them. Why? Let's say the current, let's say here is open, right? Let's say here is open. How much is IR? 0, right? Basically, this equation is works for everything. Could be no load, could be half load, could be full load, whatever, right? One case is a no load, that's I'm going to go for the load. If it's a no load, here this one is gone, right? So it said VS is equal to AVR. What's the unit for A? This is volt, this is volt. This one is a unitless, right? Because the dimension should work. Volt should be equal to volt. It cannot be volt equal to ampere, right? So, if here is shorted, right? How much is this one? 0, right? This one is 0, right? Because VR is 0, right? So, I sending end is equal to D times I receiving end, right? Again, this is an amp, this is an amp. What's the unit of D? Unitless. There is no unit for that, right? So these two, they don't have a unit. But how, let's say somehow we don't have, oh, again, go back to the short circuit, right? Go to the back short circuit. How much is this one? 0, right? So basically, VS is equal to BIR. What's the unit of B? B is going to be ohm, right? How about C? 1 over ohm, right? They call it Siemens, something. I don't know how to. I think it was this, right? This is a 1 over ohm. Right? So these two, they are unitless. So for transmission line, we have a matrix. We need to figure out what that matrix. We need to calculate A, B, C, D for that matrix, right? But we know the unit for A and D. There is no unit. They are unitless. C is a Siemens and B is okay. Now let's get to the short line, transmission line, short line. Short model is what it's called, short model. Usually less than 80 kilo ohm kilometer or 50 miles. The medium is between 80 to 250 kilometers. 250 kilometers, I think, is about 150 miles, right? Something like that. You know, between 50 to 150 miles. And if it's more longer than the 250 kilometers, we call it, long model. You have to use the long model. Now, let's focus on the short model. Short model, which we are going to use it for the next chapter, there's no chapter, the one we call it system modeling, or something like that. I'm going to use that one because that's the simplest one. I don't want to make it, complicated. In the short line model, and let's call this one. Even we don't model the capacitance of the transmission line. The one we taught you already, right? Hey, forget that one. You don't need to calculate that. Very approximate model, right? We are ignoring the capacitance in the system. And what else we are doing? We are saying we have a 50 kilometer of the line. I'm going to model it with two kind of concentrated elements. One R. I have a 50 kilometer, I don't know, the cross section is this much, this is the aluminum conductor, blah, blah, and okay, R is this much. How much is L? Is again, we go with the equation, we calculated already, it's okay, L is this much, right? And we model that that short, transmission line with one R, one X.
Why can we ignore capacitance?
So, see, I say, let's say you have $1,000 and 10 cents. Can I forget the 10 cents? No, I'm saying, but it's not 100% accurate, but it's pretty good, it's not 100%. So, as I said, you should look at the problem, Sometimes the problem is very important. The capacitance is causing the problem. We can say, hey, I'm going to ignore the capacitance, right? So let me say, during the same example, I said you have $1,000 plus 10 cents. For you, don't care, forget the 10 cents. But if it's a banking system, 10 cents is a 10 cents. You cannot, because the numbers are going to change, right? Even in 1 cent, has to be there, right? My point is, it is important what you are dealing with, right? If it's you are going, go have a sandwich, lunch, right? Then I have $1,000. My point is, here we are saying this is an approximate model. We are using very, very approximate model for this system. But if the problem we are studying is kind of related to the charge current, I cannot ignore it. Because I'm putting the problem aside, it's okay, now let's look at the problem. There's no problem. So my point is we should look at, based on what we are studying, we look at that. This is a very, very simple model. Definitely is not accurate because we are ignoring even the capacitance. And as I mentioned, these values, they are not centered. It just start from the 0 distance to 50. Everywhere when we teach the long transmission model, the long model for the transmission line, you can see you have to put it everywhere. Everywhere. It's not just in the middle or in the beginning or in the end. Now, I want to finish this one before this one goes away. If you haven't worked the time, we run out of time. This is very simple. I want to calculate the ABCD for this system, right? Let's write the equation. How much is the VS? Write the KVL, right? So VS is going to be, I'm going to call this one Z. It's going to be Z. And look at here, VS is based on VR and IR, right? So I'm going to use the IR for writing the KVL. I can use the IS or I can use the IR, right? Because I wanted to get it based on IR, I use the IR. So VS is going to be ZIR. So let's put it this way. It's going to be VR plus ZIR. How about the IS? How much is IS? 0 VR plus IR. Is it correct? Because these two currents are equal, right? These two currents are equal, right? Now, tell me, how much is the ABCD here? A is 1, right? A is 1, B is Z, C is how much? 0, and D is equal to what? 1. So I have a transmission line. If it's a short model, so the ABCD is going to be calculated like this. How to calculate Z? I'll go to chapter 4 to calculate the R and S for that. So I'm going to stop here. So the next one is going to be the medium model. They call it a high model. Basically, it's going to model the capacitance. It's more accurate than this one. We are going to go with the capacitance that we calculated in the chapter 4. And after that, we're going to move to the long model. And I'm going to talk a little bit about the stability, power flow, a little bit, not that much, how we can, transfer power between the sources and those kind of things. I'm hoping I finish everything by on Saturday. And I will have 2 more sessions to cover the periodic system and system model. I have a few questions, few simple samples, the examples to go over it, like calculating GMR, inductance, those kind of things. Maybe really like 30 minutes to go over those Saturday session is going to be again 10:30, but I'm not saying and I'll try to find a classroom, fix the classroom, she will send the email to the classroom.
Really? Yeah. It's a future.
They have a conductor in built based on seven other conductors. They are all the same circle. I'm really bad with drawing. They are the same radius. All of them have the same radius. Basically, because the middle one is a steel, the one around this one is aluminum. But let's say the radius of this one is R. And it said a conductor is composed of 7 identical copper strands, each having a radius of R. Find the G and D of a conductor. Actually, GMR. GMR. I want to know how much is GMR of this conductor. So, going back to the equation for GMR, or DS, we call it either DS or GMR. Either way, you can use it. GMR usually was for bundles and those kind of things. We use DS for this kind of thing. Either DS or GMR, doesn't matter. They're all just names, but different. Just let me find the equation for this. Going back to the equation we have for the we call it, I'm not sure how to write it, but I said, we call it either dxx or whatever, we call it is, this one is equal to root of n squared I from 1 to n, I from 1 to n, and we call it CG, di. That was what was the DS or GMR or GM. GMR or GMDS was internal for the conductor itself. GMD was when you have 2 or 3 conductors, they are some distance far from each other. So, what is the N here now? We have 7 conductors, right? 7 strings here, right? We have 7 strings. So, now let's this one is going to be something, just put it here. It's going to be something 1 over 49, right? So it's going to be flat right hand, right? It's a bringing it through. Basically, I told you that to make sure you should have 49 terms here, time each other. If you do, you have 46, 40, I don't know, 2 or something, means you are missing something. You're wrong. You know what I'm saying? Now let's just start to see what we have here. This equation is go through. Let's say this is number 1, and the rest of it. I should start from here. It's gonna go 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, right? All the possible distances. 1 to itself, we call it R prime. If you remember, for the inductors, we call it R prime. So let's figure out those things, you know. So I'm gonna start to put it here. How many of R prime I'm gonna have? See, it's gonna be 1 to 1, right? 1 to 1 to 2 to 3 to up to 7. 2 to 1, 2 to 2, 2 to 3, all the way, right? 3 to 1, 3 to 2, 3 to 7, right? So basically, I'm gonna have a 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, and 7, 7, right? I have 7 of them, right? And they are all identical here. How much is the 1, 1? R prime, right? So basically, I'm gonna have a 7 of them. So I'm gonna write R prime to the power of how much? 7, because I have 7 of them, right? They're gonna time each other. Now let's figure out all the type of distances we have here. How much is from here to here? If this is R, this one is going to be 2R, right? How many of them I have? 1, 2, 3, 4, 5, 6, right? Times 2. 12. Why? Can you tell me why?
Because there's gonna be one from the center to the outside.
Let me change this, but they call this from 1 to the center, you know. So basically, it's going to be 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. And there is a 2, 1, 3, 1, 4, 1, right? So whatever it is, you should time it by 2, right? So I have a 6 of them. See, this one is one way. I'm going from one to other. But it's a round trip, right? So it's going to be 6 of how many? 2R, right? Sorry, 2R. Because I said 1, 2, 3, 4, 5, 6. Times 2, 12, right? So I have a 2R to the power of 12, right? Now, more. Think about any possible distance, you know. The next one is going to be here. How much is this one?
2R.
2R, right? How many of them I have? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, right? Times how many? 12, because I should go other way also, right? So it's going to be times 2R to the power of 12, right? Just to check here how many I have right now. 12 and 12, 24. And 7, 31. How many I should go? 49. I need 18 more, right? Let's look at what else we have here. How about going from here to here? Right? Let's call it D1. How much is it D1? How I calculate it, can calculate it D1. Look at it. I'm going to use this one, okay? Right? This one is how much? 2R. This is 2R. And how much is this one? This is the perpendicular here, right? Your tangential, right? So basically I can calculate this one, right? How much is this one? Basically, is this one to the power of 2, right? Minus the square root of. So I'm going to calculate the D1. D1, let's do this. D1 is going to be equal to 2 times this one, right? How much is this one? Is s square root of this one to the power of 2 minus this one, right? How much is this one? 2R to the power of 2 minus, how much is this one? R to the power of 2. So basically the 4R2 minus 1R2 is 3R2, basically is going to be 2. Is it correct? do you want to do? Let's start from here. 1, 2, 3, 4, 5, 6, 7, 8,
So you got 12.
9, 10, 11, 12, right? So each of them has a 2, right? Each of them has a 2 if you look at it. So how many I have? 6. Should I go count for the middle one? No. Middle one doesn't have a middle like this, right? So basically it's going to be D1, I said how many do you have? 12, right? Did I say 12?
Yep.
Yeah, 12. So how many more we need? 36 and 7 is a 43. How many more do I need? 6. Can you tell me what's the last one?
Cross.
All the way from here to here, right? Let's call it D2. How many is D2? 4. How many of them I have? 1, 2, 3. So the other one. It's going to be 6 also. So basically, it's going to be 4R to the power of 6. Right? But let's double check to make sure we did it correct. 36 plus 30 plus 13, 49. So my numbers are correct. So now we calculate this one. That's the rest is simple, you know. And this one is 2 the square root of 3 r. So basically, you can go calculate ds for GMR. So this is how much it is. If this one is correct, it's going to be, hopefully it's correct, it's going to be 2.177. So basically, you can, oh, I forgot it. How much is R prime? Right, this one is basically 0.7788 R, right? So basically, you can replace these 7 conductors or a string with 1 conductor with this much radius. This is the equivalent of that, right? If you go look at the table I told you, can calculate it. I don't know, maybe there's 5 layer. Think about it, how much you should calculate if there's one more layer here. If there's one more layer here, see? So the next layer is going to be here. They calculated this one. I said, okay, how much? One thing is, I'm not sure if you homework or not. Sometimes this middle one is a steel. Steel is almost not conductive. When you're calculating the GMR and those kind of things, you know, you shouldn't count that one. Just for example, let's say this is a steel. Let's say it looks like this is a This one is here only for mechanical steel, nothing else. It doesn't do anything electrical. So don't count that one here. For example, if this one was this one was a steel here, I'm going to calculate the GMR for this. You know what I'm saying? This one is almost non-conductive. It doesn't have any electrical effect. It is, but almost non-conductive. So basically, you calculate the GMR for this circuit. This one is not there, but you can use this for distances to see how much it is. So basically, if this one is still, this one is going to be how many? 36, right? It's going to come up 36. Be careful. Usually for transmission line, it's not only one. Maybe there are like 6 or 7, you know, still, you know, strands, because this is a pretty long cable, very big cable. One is not going to be enough mechanical. So basically, the steel one, you ignore it. Keep in mind, if you see in the exam there is a steel you should take it out. It's not counted as toward the calculation. Hopefully you don't believe me later and say, oh, you just talked like 2 minutes in the exam, in the class, and you give it to the exam. No. I'm saying just keep in mind, if there is a steel is not counted. Now let's go for the next example. This example is the actual kind of continuation of this one. Now we have a system, we have a power system like we have a two-wire system. I have a two-wire system like this, right? And the distance is d, and d. They have a distance of d from each other. From this center to this center. It says the outside diameter of the single layer of aluminum strand of an ACSR conductor shown in figure, I think this is the figure, right? 2.8. Oh, that's good. Is 504. So he said the outside diameter of this, how should I show it? Outside diameter of this is 504 centimeters. And it's the ACSR conductor. ACSR, you know, we had this one. This is an aluminum conductor, but in the middle it has a, what it has? It has a steel. So basically the middle one is a steel. Let's go and take that to the example because just I talked about it. Now it says the diameter of each strand is now each of these. Each of these ones they have a diameter of 1.68 centimeters. Each of conductor they are like half of 1.68 centimeters, right? Now it says what is it? Determine the 50 hertz reactance at 1 meter spacing. We said if this one is 1 meter, these two they are 1 meter from each other. We want to see how much is L at 50 hertz. Not L, but X. We want to know how much is X at 50 hertz. And here it says, neglect the effect of the central strand of the steel and advanced reasons for the same. So this one is a steel. Now the middle one is a steel. The rest they are aluminum. So we want to solve the. We want to calculate how much is X for this system. It's a two-wire system. So what should I do here? First, so we're going to calculate the inductance. I don't have the equation, but it was the distance and the radius, right? Distance is there. It's a d how much? 1 meter, right? So basically, I need to calculate the ds or GMR of each conductor, right? Let's calculate it here. How much is going to be ds here for this conductor? Before going there, let me just work a little bit on this one. I'm going to make it a little bit bigger. So we know from here to here is how much it says 504, right? So, and we know each of these one is a 1.68, right? Let's calculate the derivative of this one to see how much it is. I know from here to here is how much? 504, right? So how much is this D steel? I call it D steel. How much is the D steel? Is a 504, right? 504 minus 2 times 1.68. Am I right? Because each of this one is 1.68, right? I know this one is 504. See, these are the little things I'm saying. If you don't practice it, no way you can do the exam. You have to go practice this kind of thing to be ready for the calculation. So this is a 504, right? I want to calculate this one. So basically minus this, right? These two are equal. They're 168. So if you calculate this one, I think it's going to come to the same number, 168. So it's going to make it easier for calculation. But yourself, just do it this way. This one is a R1. This one is a R2. So it's not going to be as easy as to work calculation, but I'm saying we can calculate that. So now we're going to calculate, we know basically we have let's say, we have 6 conductors, all of them they have a radius of r, and in the middle there is a hollow circle which is having the same radius again, r, right? Now I'm going to calculate the ds for this system, right? Let's calculate the ds. So how much is the ds? You guys help me calculate it. How much is the ds? First of all, it's the square root of what? Now there is it. I need 36 terms. Right? Now, tell me the easiest. R prime to the power of 7, right? 6. Because the middle one is 6. Forget that. 6. And how much is the R prime? It's going to be 0.7788 times the radius is 1.68, right? Over 2. If you are going to make it meter, it's going to be times 10 to the power of minus 1, right? Well, let's not put it in meter. We will calculate it in centimeters. We calculate it in centimeters, right? So we know the first one, 6. We need 30 more. Tell me what else we have. How much is from here to here? 2R. 2R. How many of them do we have? 1, 2, 3, 4, 5, 6, and 1. 12 of them, right? We have 2R times 2R. Sorry, not times 12, 2 power. And this one is how much? Times. So we have 18 now. We need 18 more. Tell me what we have. What else we have?
2r to the power of 12 again. And you go from the outside in.
From here to
seal
these are the columns. Let's go from here to here, right? This is 4R. How many of them we have?
6.
How many of them we have?
6.
6. Basically, we have 1 here, 1 here, 1 here. What's the power of 2? It's going to be 4R to the power of 6. Times. So how many more I need? 12. I need 12 more. The next one is going to be which one? It's going to be 2. Was it 2 square root of 3 of R, right? I'm going to calculate it again.
2 square.
2 square root of this one. Right? From here, let's put it. From here to here, right? You got the 7, right? How much was this one? 2 square root of 3, right? R. I believe it was like this, right? Can you see it from there? 2 square root of 3R. This one is 2 square root of 3R. How many of them I have? 1, 2, 3, and there's another 3 here, 6 to the power of 3 squared, right? So basically it's going to be 2 square root of 3R to the power of 12, 12, 12, 36. So I'm good, right? Let's see how much is that. Look after the calculation, we got this number. 1.93 centimeters. Now, we are going to go calculate the inductance. Because of the equation. Let's look at the two-wire system. We need to calculate it. We can maybe I can ask you to calculate the self-inductance. I don't know. We can say calculate the total inductance. All those kinds of things. You have the equation. You can bring a cheat sheet. You have all those equations. But let me see for the two-wire how much was it here. two-wire system, we had the total inductance was L total was looks like, yeah, 4 times 10 to the power of minus 7, I believe, ln of d over ds. That's what it is, right? So basically, it's going 4 times 10 to the power of minus 7 ln of, how much is it d? How much is d? Or you can say down the minus of d, but divided by 1.93. So I don't know. Because this guy is calculating a logarithmic, that's not. I think it's going to end up looking down to 1 point. I'm going to move this number. It's going to be 1.58578 millihenry per coulomb. How much is the x? What frequency do you say? 100. It's going to be 100 power. Right? So basically, this is going to be equal to this kind of curve has this much of x per clock. Somebody has to explain it.
How did you get 2 root 3 r to the 12?
How did I do what?
How did you get to the power of 12 for 2 root 3 r?
This one? This one is just how I get it. Let's just see how you do it. Whatever you have, times it by 2, because it's going to go both ways, right? For example, let's keep this one number. Let's say this is 1, this is 2, this is the 3, this is the 4, 5, 6, right? Let's start here. 2, 6, 6, 2, 2, right? So I'm going to have a 2, 4, 4, 2, right? This is 4. I'm going to have 4, 6, 6, 4, right? There's a triangle here, right? There's a 3 here times to 6. I have there is another triangle here. Right? One triangle here, one triangle here. So 1, 2, 3, 1, 2, 3, 6 times to 6.
Why did you find 100 higher for x?
That's omega.
Oh.
Yeah, 2 pi, right?
Right.
2 pi. Any question? I'm going to go one for the capacitance and we know we need to start. Well, capacitance is the same thing, you know. Yep. Which one? That would be the blood pressure. If you when you start, you have to get it right down. So it said that the next question said a 3-phase 50 hertz transmission line. This book is the Indian book, you know. The reason is using 50 hertz because on that side of the board is a 50 hertz, not 60 hertz. You know, don't be surprised why you see 50 hertz because in Europe it was 50 hertz. I know Middle East is 50 hertz, India is 60 hertz. I believe Europe was 50 hertz. But within that side of the world, you are 60 hertz. You know, when you see these numbers, don't be surprised why it's 50 hertz. You know, because it's a booking. We say if a 3-phase 50 hertz transmission line has flat horizontal spacing, flat horizontal. Let's see what does it mean. We say flat horizontal. And before solving any problem, what you should do? No, you should understand the question first. Before you start solving the problem, first you should understand the problem. Believe me, I was somewhere over the summers, this is the industry, and I'll tell you what's the problem. They have this subway train, they're electrical train, and the problem is when they don't have a regenerating system, every time you brake, you're burning the power, right? This train is moving, you have to burn that power, and you have some resistor or something, or mechanical brake or electrical brake to burn. And now they want to solve the problem. And believe me, they don't know what's the problem first, because the system they have, they think, no, it doesn't, it take care of the energy, And now they're coming with some solution for nothing. And I was telling them, okay, if what you are saying is correct, and the system is taking care of the energy, why you need to solve the problem? There's no problem to solve. You say the problem is we don't have any problem. And the other said, no, we have some problem. I said, okay, so what's the problem? Later on, I went and we drive this train, it was just under the, before, kind of starting the line, And I told them, okay, let's drive this train. And this train is connected to a DC transmission line, not transmission, DC line up there. And if you look at it, when you, this is the power electronics, all power electronics, but when you stop the train, there are induction motors in the train is driving this train. When you stop that, this motor, they change to generator. Up to this point, they were motor, they're consuming energy. Now when you are braking, they become generator, right? As soon as they become generator, they're going to start to give you the energy back. Whatever they have, they're going to start to give it back to you. So what is going to happen if you look at it? It's very simple as this, when you look at it. There is this motor, I'm going to put for DC motor, it's easier, but it doesn't matter, DC motor. This is a DC motor here. And here is your DC bus, and this is your converter. In power electronics, you learn a lot about this. But this machine is deriving, for example, there is a wheel or whatever, you stop this one. When you are stopping, basically you are taking the energy back here, right? And here there is some capacitor. What is going to happen when you put the energy back here?
Chargeable battery.
Chargeable. So what does it mean when you're charging the capacitor?
It's all Q.
The voltage is going to go up, right? When you charge the capacitor, the voltage will, what's the problem with that? If you put too much energy, the voltage is going to go too high, and you're going to start to burn all your modules, because every module has a rated voltage rating, right? So what they are going to do, inside here, they have some resistors here. This is the existing system. And even they didn't understand it, but I'm saying you need to know the problem first. So when this system can operate from 1050 to 1800 DC. This is the normal range it can go. But as soon as you get to 1800 volts, this one is there is not only one, there are many of them. So what is going to happen is going to start to burn the power, right? So basically you are putting the power here, but you are taking the power here, right? So basically you keep the capacitor balanced. You don't let it go more than 1800 volts. Some people over there, they believe this capacitance they have here is a huge capacitance. It's a huge capacitance. So when you put the power in, the voltage is not going to go that much higher, right? If you have a 10 farad capacitor, so you need a huge power to move this voltage, right? But if you have 10 millifarad, small power is going to change it. I went and looked at all their documents. The maximum they had, it was about like 200 millifarad. They had it was about like maybe it was a farad. It was a farad. But think about it. This train is a 5 wagon, and it's driving 80 kilometers. Now it is stopped. What we did, I went to the train and we drove it. I told the driver, we were driving like 80 kilometers. I told him, can you use the, initially we started to just brake the train. And we stopped, the voltage, we had all the monitoring. This voltage become 1800. So I said, okay, now let's hold on. You're 80 kilometers, can you make it, for example, 78 kilometers? Can you make it just a little bit drop in the speed, right? So still when you do a little bit drop, still you take some of this energy and bring it here, right? Even with 1 kilometer, 2 kilometers, this one again, the whole video goes right away shows, for example, was 1500 volts, it goes shows 1800. So what does it mean this? This capacitor is really small, right? Even 1 kilometer drop capacitor is enough. When I'm saying when you're going to solve something, first you know to understand the problem very well, what it is. And this is the problem with the medical. Sometimes they don't recognize the problem and they solve something they shouldn't and they make more problems, right? So when you solve a problem, when you start to solve a problem, spend enough time on the problem to understand the problem, what it is, what it's asking. And after that, you can start to solve the problem. So here, if you look at this, because I started this thing, what they need to do, they need to get it, we don't want to dissipate the power. So what they need to do, they need to put another converter here and watch this voltage. And this is like an elevator. Old elevator system, I'm not sure how much you know. The old one, when you go up, you take the energy from the utility. When you're coming down, they have a resistance to burn the power, right? Now, what they will do, they put another box here. This is called power electronics, and this is the grid here, right? They call this one inverter. As soon as this voltage goes more than something, instead of putting the power here, you take the power from here, you put it back to the grid. They call it inverter. This is DC, somebody asked me about power electronics. This is a DC to AC converter. But the control has to be very fast, very, very fast. Because think about it, it's not like you're going to drop the speed of the train 1 kilometer. You're going to go from 80 kilometers per hour to 0. So this one should be very, very fast to take all the power out. It needs a very, very good control system, control the system. There's another way. You can increase the capacitances here. Put more capacitance here, but they're bulky, they're expensive, that's another problem. You can put a battery system here. See, this is another solution. DC to DC. This is a DC to AC, you are putting it back to the grid, but here you can connect this one here and put battery here. Battery is like a storage, right? Put them here, right? Charge this battery. When your train is going to stop, it needs lots of power, right? Instead of taking everything from the grid, discharge this battery. Use it. They call it regenerative, regenerative braking, they call it. You put the extra power there when you are stopping. When you are restarting the train, again, you use the power. But this one, the problem is you have to pay a lot of money for this battery, and you're heavy. You cannot put it in the train. The good things about this one, you don't need any storage. You put it back to the grid. But there are a lot to talk about. In central, distributed, those kind of things. My point is when you start a problem, you're somewhere, they have this problem, and even they don't know what's the problem, and they're trying to solve it. And believe me, they spend a lot of money when they study, and they study even worse than they can. Because the guy studied the problem, went with something else. I'm asking you a history question, you are giving me a geography answer, you know what I'm saying? Yeah, the answer you are saying is correct, but you're not answering my question, you're answering whatever you want. That's, you see this one in industrial living, you see, people ask something and somebody else will give something else, and sometimes you see nothing happens because the guy is supposed to receive the answer, he doesn't know what he's looking for. Now, going back here, let's understand this question first. It says we have a three-phase transmission line. Here, it happens less, because here we are pretty modern country, that's a very good thing. And lots of companies, they are private. Whatever is private, is my money. I'll watch it very closely, what I'm asking and what I want. But as soon as it's government money, they waste all this. Believe me, in this country, even in this country, which is really a modern country, and we have very educated people. If you go to the government organization, I work for General Atomics, General Atomics is a defense company. You are not governmental, but you go to work in government project. And I work for a small company, like a startup company. You will see the difference the day and night. See how much they are busy. You know what I'm saying? Because the startup, the small company is private, the guy is giving the money, wants to answer exactly, I want this. But when it's government money, there is no owner, you know what I'm saying? The money is there, everybody, try to have a bite of it, and things like that. So believe me, it's a joke, but it's not a joke, but it's a reality. And it's everywhere. Here we have more private company, we see that one less. The government is much, private government is much smaller than the third world country. But for example, I'm from Iran originally, or then everything is government. They sell oil, they have oil, they sell it, the money comes in, and they and my wife worked for the government for 6 years, and she had a master's degree in industrial engineering. Believe me, she didn't learn this much during the 6 years. I told her what you can do in your resume the past 6 years, what did you do here? No, really, I'm saying this is reality. I'm saying we're giving a joke, what is not. But in general, everything is started, what's the problem, what they're being asked to solve, and let's see. Let's go to this example, I'll finish this. He said, a three-phase 50 Hz transmission line has flat horizontal spacing with 3.5 meters between their contacts. So basically, it says flat means all three on the same level. So I have one here, one here, one here, and the distance is how much? Is 3.5 meters. So the conductor are, I don't know, hard run, seven strand conductor. This one is it has 7 conductors here. Each one is like, and they are all copper. This is 7, and these are all copper. Outside conductor diameter is. This one is said the outside diameter is how much? Is 105 centimeters. So basically, I have 3 conductors, 3 phase. Each one they have 7 copper conductors. Outside diameter is 105 centimeters. And now it said the voltage of the line is 110 kV. D is 110 kV. What voltage is this? 8? Line voltage? Why line to line? It's a 3-phase system, right? By default, if they don't say anything, it's a line to line voltage. Right? So find the capacitance to neutral. You want to see how much is the C percent AN. You want to see how much CAN. And the charging current per kilometer. You want to see per kilometer. Farad per kilometer. And you want to see I charge per kilometer. You want to find these 2 parts. Basically, first we need to find the capacitance, right? And V times Y is going to give me the I charge, right? If I calculate my capacitance per kilometer, the current I'm calculating is also there per kilometer, right? So I have 3 flat conductors, like this, they are 3.5 meters from each other, and now I want to calculate the capacitance. So going back to the 3-phase system, so I need to calculate the D equal. How much is the D equal? These are not, and we are supposed they're full transposition, that what is happening, by default is there. Again, this is another thing. For a 3-phase system, if we don't say and they are not equal distancing from each other, the transposition is there. By default, it's there. Why? If it's not there, what's going to happen? The system is going to be unbalanced, right? So this one also by default is there. So how much is the D equal here? It's going to be this one times this one times this one, right? It's going to be, let's call it 1 ABC. A, B, C. It's going to be DAB, DBC, DC. Right? So it's going to be square root of 3 times 3.5 times 7 times 3.5. It's going to be 4.4 meters. So what does it mean, this 4.4 meters? Can somebody tell me what does it mean? This one is that this system is equal of a system. We have 3 conductors. We have 4.4 meters far from each other. Kind of equal distance, right? Now, the next I should do, what should I do? I should calculate the DS here for this one, right? So, how much is the R here? See, this is 2R, 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 right? 6R is this much. Basically, R is going to be 105 divided by 6, right? Centimeter. Correct or not? So you said the outside diameter is a 105, right? Outside is from here to here. 2R, 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 6R, right? So it's going to be how much? This much, right? Now you need to calculate the DS. How much is the DS? How much is the DS? Because we have solved this semiconductor several times today, we can say it very quick. Be careful, this is the capacitance. So it is the capacitance, let me write it down here. How much is the DS? First of all, 49, right? Then we have semiconductors, right? How many R prime? 7. So I should put the R prime to the 7, right? Wrong. What? This is capacitance. Check the note. It's not R prime, it's R. Check this one, for capacitance is R, not R prime. The rest is the same, Time. How many of 2R I have? 6 here and 6 here, 12. 12 times 2 is 24. So it's going to be 2R, 24 times. From here to here, it was a 2 square root of 3R, right? How many R's do you have? 12 again, right? It's going to be 2 square root of 3R, 12 times. What else do we have? 4R. How many 4R? 1, 2, 3, 6, right? I'll check this one. Let me count it first. 36 and 7. So, what? 24 is here. Just let me explain it. See here? There is a 1, 2, 3, 4, 5, 6, right? 7, 8, 9, 10, 11, 12. Right? So, we calculate the DS. What is it? Looks like calculator. I don't know because this is they have different units. I'm not gonna use this one, but you can calculate the number. Now, how much is the XN for a 3-phase system? Sorry, CN. CAN. It was, I think, 2 pi epsilon, if I remember, L and D equal over DS. If I'm correct, it was something like that. I believe it was like that. Yes. Yeah, it's the L side. It's the L. Yeah, that's right. Now, how much is the D? D equal, we calculated over there, right? That's the D equal, we have it. So it's going to be 2 pi epsilon times divided by ln 4.4 divided by what is ds, we calculate from there, right? So you can come with this number. Let me see. I used the number from this book. I believe the final number is the same. So looks like it's going to be this much. 0.00826. Okay, this is correct. Marker per kilometer. Now I want to calculate the charging current. How much is the I charge? It's going to be VAN, right? Times YAN. This, right? So how much is the VAN? Right? How much is the YAN? Is a C omega, right? C times omega. X is 1 over C omega, right? Y is 1 over X, right? Is a C omega. So it's going to be 0.00826 times 10 to the power of minus 6 times, how much is omega? Is it 50 hertz, right? Times 100 pi. C omega, right? So you calculate the number, it's going to be, looks like it's going to be 0.78 amps per watt. So this is when we ignore the capacitance for the short model, right? It is currently not that much. Right? Then, yeah. Go ahead.
I have a question. I'm not sure this has been asked yet, but when do we use R prime and when do we use R?
When you say inductance, you use R prime. When you use capacitance, you use R. See, this part is the same for both of them. The only thing is this. The only thing is this. If you are calculating inductance, you put R prime. If you are calculating capacitance, you put R. Another question? Very good.